In the next three examples, we'll look at applying the elimination method to solve nonlinear systems of equations. We can identify that the elimination method will work in this case because we have like variable terms, meaning, for instance, we have x squared and x squared, or y squared and y squared. Since we have the same variable expressions or variable terms represented in each equation, we'll be able to apply this approach. Labeling these as equation 1 and 2, we'll start off by multiplying our second equation by y, which will leave the first equation unchanged, but we will go ahead and subtract 63 to the other side. The second equation will become 20x squared plus 4y squared is equal to 84. And then adding these together will give us 21x squared is equal to 21, meaning x squared will be equal to 1, or if we take the square root of both sides, we'll get x is equal to plus or minus 1. Next, we'll take our two values for x and substitute them into either of the original two equations. In this case, we'll make use of equation 2 in order to solve for y. 5 times 1 squared will just give us 5, so this will give us y squared is equal to 21 minus 5, or 16. Taking the square root of both sides will give us plus or minus 4. So we substituted in a single value for x, and it corresponds to two different values for y. This means we can start writing our solution set. When x is equal to 1, y is equal to positive 4, and we get another coordinate pair. When x is equal to 1, y could also be equal to negative 4. So one of our x values gave us two sets of coordinate pairs that are solutions. Next, we need to consider what happens when we use our other value for x, which was negative 1. Negative 1 squared will just be positive 1, so this will actually lead us to exactly the same result. Y is equal to plus or minus 4, but gives us two new coordinate pairs to consider as solutions. In this case, when x is equal to negative 1, y can be equal to positive 4, or negative 4. So our complete solution in this case is actually 4 sets of ordered pairs, representing the 4 different points where these two equations would intersect with one another. Similarly, in example 7, we can start off by multiplying our second equation by 6, which will give us x squared plus 6xy is equal to 26. Actually, that first equation remains completely unchanged, but our second equation becomes 30x squared minus 6xy is equal to 36. So the elimination method works because in this case we're able to completely cancel out that xy term, leaving us with 31x squared is equal to 62, or x squared is equal to 2, meaning x is equal to plus or minus the square root of 2. Taking this solution, or those two solutions, we'll go back to either equation 1 or 2. In this case, we'll look at using equation 1 and substitute in our result to get the square root of 2 squared plus 6 times the square root of 2 times y is equal to 26. This will give us 6 root 2 times y is equal to 24 once we square the square root of 2 and subtract that to the other side. Or y is equal to 24 over 6 times the square root of 2. 24 over 6 will reduce to 4 over 1. And then what we can do is look at rationalizing the denominator, essentially getting rid of that radical that we have in the denominator by multiplying by the square root of 2 over the square root of 2 to give us 4 times the square root of 2 over 2, which will then reduce to just 2 times the square root of 2. So in this case, we plugged in positive square root 2, and we only have a single output, which is a y value of 2 times the square root of 2. We could repeat that process by plugging in negative square root 2. This will give us negative 6 times the square root of 2y is equal to 24, or y is equal to 24 over negative 6 times the square root of 2. This will reduce exactly the same way, except that we have that negative sign, so our result will end up being negative 2 times the square root of 2. So when x is equal to negative square root 2, our y coordinate will be equal to negative 2 times the square root of 2. In this case then, we only have two solutions, so 2 points where those two nonlinear equations intersect. In example 8, we'll need to look at updating both equations in order to get one of our variables to completely cancel out. We'll take our first equation times 5 and our second equation times 2, which will give us two new equations, 30x squared minus 10y squared is equal to 5, and 22x squared plus 10y squared is equal to 8, which will give us 52x squared is equal to 13, or x squared is equal to 1/4, which tells us that x is going to be equal to plus or minus 1/2. Substituting back into equation 1, we can drop in x equals 1/2 and go ahead and add 1 to the other side, which will leave us with negative 2y squared is equal to negative 1/2, or y squared is equal to positive 1/4, meaning that one value for x is going to be paired with two different values for y, in this case both plus and minus 1/2. Similarly, we could find out that by plugging in x equals negative 1/2 would lead us to exactly the same result. Since we'll substitute in negative 1/2 and immediately square it, the process will be exactly the same. So in this case, we have four solutions. When x is positive 1/2, we get results of positive 1/2 and negative 1/2. And if x is negative 1/2, we have those same two pairs, positive 1/2 and negative 1/2. Meaning in this case we have four xy coordinate pairs which make these two sets of equations simultaneously true.